So this is actually going to, these first couple of sections of this chapter are going to get us to the point when we merge these sections with what we did last week, will get us to actually be able to use this in a real scenario, okay? Now, will you ever use that beyond high school? Who knows? Probably not, but it'll at least give you an idea that this isn't just a bunch of hogwash, fancy relations that people put together and the math works, okay? But there's actually application, there's reason, and it drives a lot of day-to-day activities that maybe we're impacted by, but maybe we don't participate in them. Does that make sense? Okay, do you, anybody get stuff from Amazon? Okay, so like distribution centers will use this type of stuff. UPS will, and FedEx and those kinds of places, they will try their best when they make routes for their drivers to minimize left turns. So they want to take as many right turns as they possibly can. Anybody know why? Why would I want to take a right turn versus a left turn? If I'm at an intersection, why take a right turn versus a left turn? So if I take a right turn, I stay on the same side, so I don't get in a wreck. I don't cross traffic when I take a left turn or when I take a right turn versus a left turn, right? So UPS and FedEx want to do that. Also, when I take a right turn, I think maybe you're getting onto this. If I take a left turn, it's a longer arc, isn't it, than a right turn? So it's more gas. Yeah, yeah. So what they do, so the idea is if I've got, like let's say I've got, like this is my map or whatever, and I've got like boxes to be delivered like at these spots, okay? They will do their best to kind of create a route. So I take a right turn, right, right? Okay, maybe that would be a left turn, but then that's a right turn, and then I go on to my route. So instead of, and there's a lot of different, maybe I could go there. There's a lot of different routes I could take to get those boxes, right? But they're going to try to set up the ones that are most right turns possible, and that should then minimize chances of getting in accidents and minimize the amount of gas. Now, it doesn't say that they're going to use only right turns, but they try to maximize the amount of right turns. Say again? Yes. Yep. We cool with that? Get me double guessing myself. All right. Okay. So in doing this, we need to talk about solving systems by graphing. Okay. Just some key terms here we've talked about in the past, but just reiterating them. A system of equations is just a group of equations. Okay. Now, it's a group of equations having the same variables. And for us, they're usually X and Y. Okay. Now they don't both, just traditionally, they don't both have to have an X and they both don't have to have a Y. But if one of my equations only has X or one of my equations only has Y, it's a really easy system to manipulate. So usually both of our equations will have X and they'll both have Y. We can talk about, what if they all have X, Y, and Z? And then I would actually need 3 equations. So however many variables I have is how many equations I will also have. So if I have, if you have 2 variables, it will yield 2 equations. If you have 3 variables, it will be 3 equations. If you have 4 variables, you'll have 4 equations. So usually what we write is that if we have n variables, we will have, that will yield n equations. EQN for equations. Yes? And. Yeah. for the most part, we're going to deal with just two. We might see the occasional 3 variable, but if we do that, we'll use a calculator to help us with that. Okay, it'll be much easier. Okay, solving 3 variable equations is a very tedious process. Okay, time consuming. A solution of a system of linear equations is any ordered pair that makes all of the equations in the system true, or it satisfies all the equations. Okay, it's any point that satisfies all equations in the system. If 2 lines intersect, something from geometry, if 2 lines intersect, then they intersect where, or at what? At a point, right? At one point, right? Okay, we had a postulate in geometry said, when 2 lines intersect, their intersection is exactly 1 point. That 1 point is the solution to our system of equations. Okay? So here it says the solution of a system of linear equations is where the 2 lines intersect. The point of intersection will be the point on each of the lines within the system. All right, so this is just a demonstration of what we're doing graphically to find a solution. And then in the next couple days, we'll remove the graphical part of it and we'll just do it algebraically. Okay? But everything we do in the next couple days algebraically, in the background, behind the scenes, this image is taking place, or an image like this. Okay? So, everything that is blue, every point on here that is blue, works for this blue equation, satisfies that blue equation. Okay? So there's a point like 1, 1 on here. Okay? So 1, 1. If I plug 1, 1 in for the blue equation, okay, plugging in for the blue equation, I'll do that. Let's do it this way. If I plug 1, 1 in for this blue equation, does that give me a true or false statement? I plug 1, 1 in, I get 1 equals 3 times 1 minus 2. What's 3 times 1? 3 minus 2? 1. Is 1 equal to 1? So it gives me a true statement. Okay. If I try the point, let's try 0, x to be 0, y to be negative 2. Same idea. If I plug in negative 2 here, 3 times 0, and then minus 2. What's 3 times 0? 0. Minus 2 is negative 2, right? Is negative 2 equal negative 2? Yeah. So every one of these points is going to be like that, right? Okay. If I try, let's try this point right here, 2, 4. So the y is 4. The x is 2. 3 times 2, 6 minus 2, 4. Is 4 equal 4? Okay, so 2, 4 was also true. Okay. Now, what I'm going to do real quick is I'm going to do the same exact thing. But do it with the red one. So if I got x and y and true or false. Okay. If I were to pick any number or any ordered pair off the red one, like negative 3 as x, negative 1 as y. So negative 1 equals negative 3 plus 2. Is that a true statement? Yep. Okay. If I plug in x to be negative 2, y to be 0. 0 equals negative 2 plus 2. That's true, right? Negative 2 plus 2 is 0. Okay, so any one of these red points that I choose is going to give me a true statement, right? Now, if I take a blue point, and plug it into the red equation. So let's just take that blue point right there, 0, negative 2, and plug it in for the red one. So So we get 0, -2 is the ordered pair. Is -2 equal to +2? That'd be false, right? Okay. And if I plugged in a red one, like -1, 1 into the blue, -1, 1 into the blue one, so 3 times -1 minus 2, well, that's -1 does not equal -5, right? So that would be false. Okay, so hopefully that demonstration there shows me that any blue point that I choose that comes off the blue line should plug into the blue equation and say, or give me a true result for the blue equation, right? Any point that I pick off the red line should be able to be plugged into the red equation and give me a true statement for the red equation. And those last two examples we did, anything plucked off the blue line, plugged into the red will give me a false, right? And anything on the red one, plucked off and plugged into the blue equation, will also give me a false. Except that point right there. That point right there, we've already seen 2, 4 right there giving me true on the blue line. If I plug 2, 4 in on the red one, y is 4, x is 2. Is that a true statement? So 2, 4 gives me true on both of them. Of all these lists that I could create of ordered pairs that came from the blue and came from the red, all the ordered pairs that give me true statements are going to be different, except for that one of 2, 4. Because if I look at that, is 2, 4, is it on the blue line? Is it also on the red line? So it's on both lines, right? It's the only point out of all the points that exist that is on both. So that is what we refer to as the solution of this system. Okay? So 2, 4 is the solution to that system. Yes? I'm sorry. Okay, so when we are being asked to graphically solve a system, we are going to graph both lines. So this is a practice in what we learned in Chapter 2. Just going to kind of revisit that stuff for several days, several sections. And just when we're done, we're going to see where they overlap. Okay, now the only thing here is that to really get a good solution and an accurate solution is when you graph, you're going to want to make sure that you kind of do a good job of it. Okay, I know a lot of people, and I'm guilty of it too. If I graph this first one, I'll do that, and then my line will suck, right? Well, if I'm looking at two lines that are intersecting, and they both are kind of like just terrible, I can see where they cross. But if I was to do a better job of graphing, maybe they really cross like right there. Does that make sense? So you got to be cautious of the human error that gets created when we do this stuff by hand. Okay, so y equals 2x plus 4. So we're going to graph that one first. Okay, so what is my y-intercept? 4. Okay, that's your y-intercept. So that's where you cross the y-axis. So I'll go up to positive 4. Okay, now what is the 2? That's the slope. And it's 2 over 1, right? And they're both positive, correct? And you ran into this issue, and it's just the way Math Excel works. And in the example that they gave you, I think maybe it was on the quiz on Friday, where it says you can't, like, right now, if I want to go up 2 and to the right 1, I've got to extend things, right? I got to extend my graph. When you're in Math Excel, it wouldn't let you do that. You could either type your points in or you could plot it using the cursor, and it wouldn't let you do that. But going up to right 1, is that the same thing as going down to left 1? Negative 2 divided by negative 1 is still a positive slope of 2. So I can go down to left 1 and get the point that I need to help me graph this thing. And if we do it correctly and try to minimize as much human error as possible, you'll see that even though as I extend this, so try to eliminate as much human error as possible. So I try to get that to go through those points the best I can. If I go up to over 1, it'd be about where my cursor is, right? So it is, even though I didn't go up to over 1 to get that point, when I make the line shows me that that point would have been right. Now the only thing is that when you're doing a system and you're going to put two lines in here, I get a lot of people that will like cut their lines off like this. Okay, just make them go, because your other line might like come down through here, and you might not get an intersection if you don't extend your line all the way through the graph. So just extend your lines at least through the portion of the graph that is visual to you. So that's y equals 2x plus 4. Okay. Now we're going to go graph y equals x plus 2. So what is my y-intercept there? 2. And then where am I going to go from there? Up 1, right 1, right? Up, right, what? Up 1, right 1, up 1, right 1, as many times as you need to do that. And then we're going to connect those. Okay. And now we can see it. Those are going to intersect right there, correct? That ordered pair is x being -2, y being 0. X is -2, y is 0. And that should allow me then to say, okay, well, does that work? Does that give me a true statement right there? If I plug -2, 0 in. So x is -2, y is 0. Is that a true statement? Yep. So that's true, right? 0 is equal to 2 times -2 plus 4. That's -4 plus 4. That gives you 0. It should also be true here then. So if I get y to be 0, x is -2, add 2 to it. Does -2 plus 2 give you 0? So that is true. That is the only point out of all the points that exist. That is the only point that's going to give a true statement for both of those. Okay? Any other point that is on the red line, will give me a true statement for the red equation, but a false for the blue one. Okay? Anything that is on the blue line, will give me a true statement for the blue equation, but a false for the red. And then anything on neither line, so like maybe that point right there, would give me false for both of them, right? And then obviously this one will give me the true for both of them. Okay. Now, something that might be of use to you, graphing at least. Okay. If we go to Desmos, okay, now obviously in Math Excel, you're going to have to plot your points and that kind of stuff, and graph your line. But if I go y equals, was it 2x plus 4? And we have y equals x plus 2, okay, generates those graphs pretty quickly for us, correct? Click on where you think they intersect, and it will show you where they intersect. That make sense? Okay. If we, I don't know if I can generate a table. No. Should be a way somehow in this to be able to generate a table that creates kind of like the table that we saw. There we go. The table's here, but I'm not all that versed in Desmos as well as I should be with that component. Okay, so when we have two lines, whenever I give you two lines, there's actually three different solutions that can exist. Okay, the one solution that we just saw, the example we just saw, is the most common. Okay, probably 95% of the questions that you get are going to be that type. Okay, which is the one solution that we see there in that first graph. Okay, another type, I'm going to jump over to the one on the end here. It says no solutions. What are those two lines there? They're parallel. Okay, so when we're doing the work, and here's why we talked about parallel lines in the last chapter, is that if I'm doing the work, they could say graph these two lines and figure out the solution, but I recognize that my coefficient for x is the same in both lines. Okay, then I automatically know that these things are going to be parallel, and there are no solutions. Does that make sense? So I don't have to run through all the work if I can make that connection that the slopes tell me that the lines are parallel, and then that would mean that the lines do not intersect. So there's no solutions there because they do not intersect. Now, that middle one, you see we've got, if we zoomed in here, I've got red over blue, right? Or blue over red, okay? And that means, and this happens very rare, but it does happen, the actual lines they give you are the same line, okay? And then therefore they intersect everywhere, okay? So here's an application of this, okay? It says scientists studied the weights of two alligators over 12 months. The initial weight and growth rate of each alligator are shown below. After how many months did the alligators weigh the same amount? Okay. So this first one says alligator 1, its initial weight was 4 pounds, and its rate of growth is 1.5 pounds per month. So rate of growth, that's the thing that's changing, right, after a month. So after 1 month, it's 1.5 pounds. 2 months, it's 3 pounds, right, total. After 3 months, it's 4.5 pounds, okay? So if I want to make the alligator's weight y, that's what they're saying here, let y equal the alligator's weight, and x be the time in months. Well, if I go 1.5 and multiply it by x, and x is the number of months, so after 1 month, that's 1.5. After 2 months, it's 3. After 3 months, it's 4.5, right? Okay. That's going to give me the weight if they were born at 0 pounds, right? But nothing's born at 0 pounds. Born at 4 pounds, right? So if I take those and add, so take 1.5x and add my initial weight of 4 pounds, that should tell me how much my alligator weighs after 1 month, 2 months, 3 months, 4 months, right? You guys take a minute and come up with alligator 2 using the same logic. Figure out the weight of alligator 2, the equation for the weight of alligator 2. Just for graphing purposes, I took the 1.5 and rewrote it as 3 over 2 for this first one. So alligator 2, what's the coefficient that's going to be in front of your x? 1. And then you're going to add to that 6. Okay. A lot of times what I like to do is, it's not a huge deal, and this is just for my organization. I like to put like little subscripts to remind myself that this is for alligator 1, put the 1 there, alligator 2, put the 2. If I had names for the alligator, I'd put like the letter of the first letter of their name right there. So I just remember what equation I created or built correlates to which alligator. So now when we graph these, because I'm only interested in months being positive numbers, right? Okay, months can't be negative, so time elapsed is always positive. So that's why I'm only looking at the first quadrant here. But if we plug this stuff in, let's go ahead and graph. We'll do it in, graph this one here in red. What's my y-intercept for that one? 4, right? And now we're going to go up. If you left it as 1.5, you would go up 1.5 units and then over 1 unit, right? So it'd put a point like right, I'll put an X right there. I know it's kind of hard to see. Let me zoom in. So if I left my slope as 1.5, okay, because it's 1.5 over 1, right? So up 1.5 and over 1. And that's fine, but I kind of had to guesstimate where 0.5 was, right? If I change it to a fraction, 3 over 2, because that's still 1.5, then I go up 1, 2, 3, over 1, 2, and I know exactly where that point is, and there's no guesstimation, right? Just going to do a couple more of those, up 3 over 2, so I can get a good line. You can even see here, if I guessed where 1.5 over 1 was, I actually kind of put that point in a bad spot because it missed the line, right? Okay, which you might think, well, yeah, but it was very tiny. But what we find out, guys, is that over a long distance, that little miss there gets exasperated. Okay, it gets much bigger. Has anybody ever done like construction work or anything like that with mom or dad or anything? Ever cut like plywood or anything like that? Okay, if I have a sheet of plywood or drywall or something like that, and I want to cut this thing, so they're 8 feet by 4 feet. Let's say I want to cut this thing so that's 8 foot by 3 foot. Okay, I would measure like a foot down there and make a mark, right? Well, if I come over here, like right there, and measure down 1 foot, okay, and if I'm off 1/8 of an inch or 1/16 of an inch, and I connect my line, okay, my line is going to deviate, and it's going to be greater than 1 foot over here when I get done. Does that make sense? Okay, so what I want to do is actually I want to measure 1 foot there, but then come over here and measure 1 foot, and then connect them that way. Does that make sense? Okay, and that's the same error that is happening here if I had to kind of guess where this 0.5 was. Okay, and that's just human error that we try to minimize. Now the next one, my y-intercept there is going to be what? 6. And then from there, where are you going to go? Up 1 to the right 1, up 1 to the right 1. Keep doing that as many times as you need to. Okay, so now we see where they cross, right? So these things are crossing at an x value of 4 and a y value of 10, right? So that ordered pair is 4, 10. So what does that information tell you? Well, what was x representing in our equations? X was the time in months, right? And y was the alligator's weight. So right here, that number is months. That number is a weight. And what we're seeing there is that these two alligators at 4 months both weigh 10 pounds, right? Okay. Before that, the blue alligator, okay, before 4 months, the blue alligator was heavier. Because would you agree that the blue line is above the red line? And after 4 months, the red alligator becomes heavier because its line, or that line of the red alligator, is above the blue alligator. And that's all the interpretation and analysis that we can get from that information. Questions on that? Does that make sense? Okay. So a lot of you probably not going to measure alligators, right? In your lifetime, Noah? You ever going to? Probably not. Okay. Give this one a shot. Okay, so I don't know, like, my car is so old and janky that my radio doesn't work, so I don't even care about radio. But like, do people still do satellite radio, like Sirius or not Sirius, Sirius radio? Anybody still do that? Is that a thing? Okay. So that's what this is talking about. Okay. You can do this with cell phone plans. Okay. Is Sprint better for me, or is Verizon better for me, or T-Mobile, or whatever? Okay. We can analyze all of them. So it says one satellite radio service charges $10 per month plus a one-time activation fee of $20. A second service charges $11 per month plus an activation fee of $15. In what month will the cost of the service be the same? And what does this point mean? Okay, so let's let y be the cost. We'll just say total cost, and x be the number of months. So service number one, I want you guys to write an equation, see what you can come up with using this information here. See what you come up with for the equation for service number one, and we'll talk about that in a minute. All right, so what we come up with, what is the thing that is changing here? But if I just look at the blue, is it so an activation fee, like that's like a one-time, so it's the one-time activation fee. So you only pay that once, right? How many times do you pay the $10? Every month, right? So after 1 month, I pay $10. But if I wait for 2 months, then I pay $20, right? If I wait for 3 months, it'd be $30, right? So the per month is the thing that's actually changing. So I'm going to write this as y equals 10x plus 20. Does that make sense? And the idea then is, and just to make sure this makes sense, if I go 0 months, the moment I activate my line, I have to pay $20 just to activate it, right? And if I go after 1 month, then I had the activation fee, which was 20, but now I've paid $10 to have it service for 1 month, so now I've paid $30 total, right? If it's 2 months, I paid my original $20, and after 2 months, I paid first month and second month, so that's another $20, so it's 40 total. So that should give me the cost, the total cost that I've paid for that service after so many months. Okay, that's not what I'm paying every month, right? Every month I'm paying just 10x or just $10. Okay, that's what I've paid total as I've kind of owned the service. The next one then is $11 for every month that elapses, plus an initial 15, right? So the idea then is, okay, well, if I go like 0 months for both of these, so 0 months, try to do these color coordinated. So if I go 0 months for the blue service, I'm going to pay $15. That's my activation fee, right? And the red one would be $20, right? So if I'm just interested in just activating this, the cheapest one for me would be the blue one, right? But if I go 1 month, if I pay for 1 month, I've paid here a total of $30, right? But down here for 1 month, I've paid 15 plus 11, which would be 26, right? Which one's cheaper for 1 month? The bottom one, right? The blue one. So if I'm interested, like if I know that so these two scenarios are laid out in front of me by these two companies, and I know that, hey, I'm only going to have this service for a month. I'm only interested in it for a month. I do this with the Hulu TV and YouTube TV and stuff like that. I only have TV so I can watch baseball during the summer. So I try to figure out, okay, well, the activation fee, monthly fees, which one's cheaper? Okay, if I'm going to have it for 3 months or 4 months or 5 months, whatever. Okay, so this is the type of thing you can do. If we go to Desmos, we can actually see. So this one is 1 and 30, 1 and 26. Let's see if when we go to Desmos, for some reason I closed it. if we go y equals 10x plus 20 and y equals 11x plus 15, okay, now they look like they're parallel, and it's just because 10x and 11x are pretty close to one another, right? Okay, but there are different slopes, so they're not parallel. So I can start moving around my graph just by clicking and dragging, and you can see here that they do indeed intersect right there. Does that make sense? Okay. If I zoom in far enough, you'll be able to see that the two lines are different, except for right there, they're the same. So at 570. So we want to know what is, so 570, if we graph both these, 570 is the solution. Remember what X was. X was the month, right? And 70 was the cost. So at the 5th month, or at the conclusion of the 5th month, I have paid in both services the same amount of $70, right? After the 5th month, one of those is going to be more expensive than the other. Okay, before the 5th month, one is more expensive than the other. We see before the 5th month that the red one was more expensive, right? At month 1, it was $30 for the red one. At month 1, it was $26 for the blue one. After 570, after the 5th month, the blue one is going to become more expensive, and the red one's going to be cheaper. Does that make sense to everybody? So as you're a consumer and you're trying to figure these things out, which one do I go with? Something to keep in your mind is, do I have knowledge of how long am I going to have this service? If I'm going to have this service for a year, 2 years, 3 years, even though initially it's going to be more money out of my pocket to go with the red one, if I keep that service for 2 years, I'm actually going to save myself quite a bit of money going with the red one. Okay. Cell phone bills are that way. Cell phone plans are that way. Cable, all that stuff. Okay. There is an assignment in Math Excel. Okay. Yes, due Wednesday. There's going to be some questions on there that, like the examples that we did so far, all the lines were like y equals, right? There's some questions on there that are like 2x plus y equals 10, and they ask you to graph. Okay. So use those strategies. We'll talk about a couple of them tomorrow. But if you get going on that tonight, you're going to use some strategies from the last couple sections.